So let's graph tangent. Tangent is different than sine and cosine. It has a different period. It has a different shape altogether. And when I'm graphing tangent, I'm typically thinking about plotting these values. So the coordinates I'm going to pick for x are the angles 0, pi over 4, pi over 2, 3 pi over 4, and pi. Because the period of tangent isn't 2 pi, it's just 1 pi, which is kind of interesting. The tangent graph goes through all of its values from 0 to pi, so from 0 to 2 pi. But it's because tangent is a quotient, and tangent is sine over cosine, and sine divided by cosine from quadrant 1 to 2 goes through kind of all the values you can possibly take on, and then it starts repeating. So tangent to 0, well, that's going to be sine of 0 over cosine of 0, which is 0 over 1, which is 0. And let's scale this appropriately. I'm going to make this 1/2. This is 1. 3 halves. It's negative 1/2, negative 1. And then tangent of pi over 4 is 1, right? It's sine of pi over 4 over cosine of pi over 4. But sine and cosine are the same at pi over 4. Zoom in a little bit here. So pi over 4, which is halfway between 0 and pi over 2, the tangent value is going to be 1. And then at pi over 2, I'm going to get sine of pi over 2 over cosine of pi over 2, which is 1 over 0, which is undefined. So it's kind of interesting to think about what's happening here, actually. As the angles get closer and closer to pi over 2, what's happening to tangent? Well, tangent of your angle x is sine of x over cosine of x. And as x gets closer and closer to pi over 2, the numerator is getting closer and closer to 1, and the denominator is getting really, really small. So we have as a fraction where you have something on top that's close to 1, and something on the bottom that's getting smaller and smaller and smaller, meaning the fraction is getting really, really large. So what's happening is as we go towards pi over 2, the values of tangent are getting infinitely large. And we have a vertical asymptote. This is looking kind of like this. We could plug in more values if we wanted. Right? We could plug in pi over 6 here. And tangent of pi over 6 is root 3 over 3, which is about 0.86. And tangent of pi over 3 is root 3, which is about 1.7, which my graph might not look perfect here. Sometimes it's hard to make it look perfect. On the other side of pi over 2, tangent starts being negative. Right, from pi over 2 to pi, we're in quadrant 3. Tangent of 3 pi over 4, that's going to be, again, sine of 3 pi over 4 over cosine of 3 pi over 4. They're the same values, except sine is positive and cosine is negative, so we're going to get negative 1. And tangent of pi is going to be 0. Sine of pi is 0, cosine of pi is negative 1. So on the other side of pi over 2, we have a vertical asymptote that's going down to negative, and it's going to look like this. So there's one not nice period of tangent. If I was, well, we'll talk about that in a second, actually. So I don't want to just finish there because the graph kind of goes on, right? You can only draw one period, but you can also draw more. It's going to continue doing the same thing from pi to 3 pi over 2 as it did from 0 to pi over 2. So it continues on this way. At this point over here, 5 pi over 4, we get the same value as pi over 4. And it does the same sort of thing. It just repeats this one period over and over and over again. Now, if I were drawing one period of tangent, I probably wouldn't pick any of this actually. I probably would, well, that's not true. I would not pick any of this. I would pick the section that starts over here at negative pi over 2. So here's my vertical asymptote at x equal to negative pi over 2. And I would draw the graph looking like this. So it goes like that. So just to show you guys a little bit more nicely, here's a couple periods of tangent. If I was graphing tangent, if I said graph one period of tangent, here is the very not detailed graph I would draw. I'd throw up a vertical asymptote at pi over 2, a vertical asymptote at negative pi over 2. Make sure I hit the origin, and that's kind of about it. There's one period of tangent, and it's a little crooked. Sometimes your graphs are crooked. It's all right. And then you could draw more, right? It keeps going on and on and on, but we don't need any more of it. So if anyone ever wants to draw one period of tangent, this is kind of the usual period of tangent people draw from negative pi over 2 to pi over 2. Then I would not say that. I agree. It does. So someone asked, the tangent is basically x cubed. Not exactly. It has a similar-ish shape for one period of it, but let me actually, just so you guys can really, so I can not just tell you, but actually show you. Let's look at the difference between them, because I will say you're not the first person who's ever made that observation for sure. And yeah, it does kind of look like that. So here is x cubed. Lovely, great graph. Kind of looks like tangent, although I will point out it is a lot flatter at the origin than tangent is. Tangent is a lot more diagonal. And here is all of tangent. There's a lot, I mean, so you're right. In the middle here, in fact, if we just restrict ourselves to being between negative pi over 2 and pi over 2. Oops. There we go. They look pretty similar. I mean, you can see they do look different at the origin, but they have a similar shape. But definitely there's a lot more to tangent, right? If we get rid of this domain restriction, that's tangent, right? There's a lot of tangent. It keeps going and going and going. And x cubed has a bit of a different look. So similar, but not the same. Yeah, good point. Other observations or questions about tangents? We don't do a lot with tangent, but it's a graph you should kind of have seen. So I'm not gonna ask you a whole lot about it, but I want to, here's the tangent. I want you to see it. I want to close it. And then if I was going to graph negative tangent, I'm just going to take my graph and flip it over. So I'm trying not to do all the work in the world, meaning I don't really want to plot all these points. I want to be like, okay, tangent of 0 is 0. The next point I'm thinking about is pi over 4. Tangent to pi over 4 would be 1. Negative tangent to pi over 4 is going to be negative 1. And then I know I've got a vertical asymptote at pi over 2. And I'm going to have vertical asymptotes at every odd multiple of pi over 2. That's always true for tangent. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, et cetera, et cetera, et cetera. We're always going to get a vertical asymptote there because that's where tangent is undefined. Tangent of 3 pi over 4. Well, normal tangent of 3 pi over 4 would be negative 1, but it's negative tangent of 3 pi over 4 is positive 1. So I'm just taking this graph here and flipping it over. So it's going to look like this. Sorry, I'm trying to come out the right way. I will like that. Come down this way. I will point out when it goes through the origin here, or whenever it goes to the x-axis, it does kind of look like it's got a slope of about 1. That's true. It does have a slope of about 1 when it goes to the origin or through anywhere on the x-axis. And then we keep going this way. And your results may vary depending on how good or not good a drawer you are. I don't think it's a crime to look at Desmos to see if your graph looks relatively decent. So that's tangent. That's negative tangent. You should be somewhat familiar with its graph. I wouldn't say too much about it really. The only thing we really like to do with tangent is kind of shift it left or right or change the period length. We'll talk a little bit more about that on Wednesday. On Wednesday, I'll also show you the graphs of cotangent and secant and cosecant. They're not things that are like, right, I'm trying to give you a broad view. I don't want to inundate you with details that aren't super important. I do think secant and cotangent are mildly important. You should be aware of them, but they're not the most important. So we're going to talk about the more important things before them. So there's your graph of tangent and moving on. That's kind of it. Tangent, bye. Here is a much more useful thing to talk about. Solving trigonometric equations. So let's say we wanted to solve sine x equal to the square root of 3 over 2. We know many answers to this equation because we know many angles where sine is equal to the square root of 3 over 2. So when I'm doing something like this, there are two things I think about. What's my reference angle? And what quadrants do I want to be in? So what angle can I take sine of and get root 3 over 2? Say it one more time. Yeah, exactly. And that should be more specific. Yeah, in the first quadrant, right? What reference angle? The angle is definitely pi over 3. But sine can be positive root 3 over 2 in more than one quadrant. It can be positive root 3 over 2 in quadrant 1. What other quadrant will be okay? Quadrant 2, exactly. Sine is positive in quadrant 1 or quadrant 2. So if I was going to answer this question, my solutions would be x equal to pi over 3 in quadrant 1 and x equal to 2 pi over 3 in quadrant 2. I want to point out, if you were to use a calculator here and just take the inverse sine of root 3 over 2, you wouldn't get the whole picture. That's the other thing I'm going to address on Wednesday, but I'll just say right now. If you were to do the inverse sine of root 3 over 2, you would get just pi over 3. Or if it was in degrees, 60 degrees. You could do that to help you find all the answers, but when you're solving an equation, it's kind of like the difference between taking the square root of 9 versus solving x squared equal to 9. Square root of 9 is just 3. That's like taking the inverse sine of something. You get one answer. Whereas solving this equation, sine of x equal to root 3 over 2, is like solving the equation x squared equal to 9. You can take the square root to help you solve it, but the solutions, plural here, are x equal to 3 and x equal to negative 3. So when we're solving trigonometric equations, most of the time there is more than one answer. There's more than one angle that solves the equation. So let's look at this next one. Trying to solve cosine of x equal to negative root 2 over 2. What's the reference angle in the first quadrant that's going to be useful to me here? Is it pi over 3, pi over 6, or pi over 4? Definitely pi over 4, right? Because we know that cosine of pi over 4 is positive root 2 over 2. In fact, let's write that down. We know cosine of pi over 4 is positive root 2 over 2. Pi over 4 isn't going to be one of my answers, right? It doesn't solve the equation, but it is the reference angle I'm using to help me figure out what's going on. So now I need to think about what quadrants my answer should be in. So the quadrants are where cosine is going to be negative. Not quadrant 1. Say that one more time, Erica? Totally could be 2. What other quadrant shouldn't it be? Not 4. It should be 3. Yeah. So we were looking for an angle in quadrant, in quadrant 2 with a reference angle of pi over 4. That's interesting. I don't know how that happened. I didn't touch anything. Go away. Thank you. Thank you. So depending on how you want to do this, right? You could say, well, in quadrant 3, my reference angle is pi over 4. So my actual angle is going to be pi minus pi over 4, which is 3 pi over 4. And that's in quadrant 2. And then my other one's going to be in quadrant 3, pi plus pi over 4, which is going to be 5 pi over 4. And those are my answers. So when I'm solving trigonometric equations, I want to find the reference angle and then find the appropriate angles in the quadrants. Now, I should point out, when we're finding these solutions, we are always asking the question in a way where we are limiting ourselves to our angles being between 0 and 2 pi. So we're not going to look for, right? Technically, if I said solve this equation, there's an infinite number of answers, right? X could be 3 pi over 4, or 5 pi over 4, or 11 pi over 4, or 13 pi over 4, right? You can just keep adding on a whole period's worth to get more and more answers. We're not going to do that. If someone did do that, so I will just point out, if we wanted to find all the solutions, the way that would look is annoying, but an easy way of writing it would be 3 pi over 4. Thanks. Sorry. Plus 2 pi k, where k is an integer. And also 5 pi over 4, plus again 2 pi k. That's the way you write all the possible answers if someone's not limiting your domain. But typically, right, you're not saying you know a whole lot more with this, right? You say, well, yeah, I know I can add on 2 pi or 4 pi or 6 pi or 8 pi and get another angle that's going to have the same cosine value. But it's not really any different than we've already done. So let's up the ante a little bit. So we're choking on water. Sometimes we're going to have to do some algebra before we can actually solve these things. So if I want to solve, some algebra here, sine of x plus 1 equal to 0, there's a little bit of work I have to do. I'm going to set sine of x equal to -1. Now, this is an example of an equation that actually doesn't have a reference angle for it. Right? Sine of x equal to -1, that's one of those quadrantal angles. And we just need to know where on the unit circle we need to be so that the y coordinate's -1. So I don't want to be at the top, the bottom, the left, or the right. The bottom, right? The bottom is where the y coordinate, which is the sine value, is equal to -1. And the angle associated with that is not 0, not pi over 2, not pi, but 3 pi over 2. And that's the only answer. Yes.
I have a question really quickly.
Go ahead.
The page before.
Sure.
I don't know if it's just I mixed it up or something, but how is pi plus pi over 4 3 pi over 4?
Oh, sorry, that's pi minus pi over 4.
Or for the next one.
Sure. So pi plus pi over 4. So what I'm doing here, what I'm not showing is I'm not showing the getting of a common denominator. So really what's happening here is we have 4 pi over 4 minus pi over 4. And then 4 pi minus pi is 3 pi over 4. Same deal here. This is 4 pi over 4 plus pi over 4. Come on. All right. Just a quick aside here. if you were to do this, right, if you were to say, instead of going this way and just knowing what the angle is, if you were to say x was the inverse sine of -1, it wouldn't give you that answer. The calculator, if you use a calculator for that, calculator is going to give you -pi/2, which is coterminal, right? They both live in the same spot. 3pi/2 counterclockwise around and dip there, -pi/2 clockwise gets you there. But this answer is different from that answer. And since we said we wanted our answers to be between 0 and 2 pi, it's really important that this is the answer we give and not that one. You can certainly use a calculator to help you figure out what the answer should be, but want to make sure your answer lives in the right domain. Okay, let's look. And you should always, if you have questions, stop me. But I'm going to move on to the next one. Tangent squared equal to 1/3. I should definitely take the square root of both sides. I mean, there's other ways you could do this, but taking the square root of both sides is what I think is the nicest here. So I'm going to have tangent of x equal to plus or minus the square root of 1/3. Now, that doesn't look like a number that's really obvious at first, so I need to simplify it. So I'm going to write this as plus or minus the square root of 1 over the square root of 3. And that's plus or minus 1 over root 3, which does look like a tangent value that sticks out to me, right? There are angles we know where tangent is equal to that number. Or if you rationalize it, plus or minus root 3 over 3. Okay, this one's kind of fun. What's my reference angle? Is it pi/6 or is it pi/3? I know it's not pi/4, right? Because I know tangent of pi/4 is 1. I think it's pi/6, right? So what I have to remember is tangent gets bigger as the angles get bigger. Tangent of pi/6 is root 3 over 3, and tangent of pi/3 is just root 3, which is a larger value. So my reference angle is definitely pi/6. Here's the fun part. Fun. What are my quadrants? It is definitely all of them, because tangent can be positive or negative. That's true in every quadrant. Quadrant 1 is positive, quadrant 2 is negative, quadrant 3 is positive, quadrant, right? So all quadrants. So in quadrant 1, we get pi/6. What's our answer in quadrant 2? Something over 6. We're all over 6. 5 pi is one of them, yeah. Eric, I said 7 pi/6. There's one more. It's 11. And I'll point out, it's all of the fractions that wouldn't reduce. It can't be 2 pi/6 or 3 pi/6 or 4 pi/6 because those all reduce. It can't be 8 pi/6 or 9 pi/6 or 10 pi/6 because those all reduce. Pi/6, 5 pi/6, 7 pi/6, and 11 pi/6 are the 4 from 0 to 2 pi that don't reduce at all. Or you could also say pi/6, and then this is pi minus pi/6. That's pi plus pi/6. And that's 2 pi minus pi/6. Right? They're all just pi/6 away from the x-axis in one way or another. So having done that, says to me that the next one's going to have a similar answer in that we're going to get answers in every quadrant. Since cosine squared equals 1/4, if we square root both sides, we're going to get plus or minus something. I want to do this one slightly differently to show you another way to tackle it. So instead of square rooting both sides, that's dumb to do it this way. I was going to like multiply both sides by 4 and then do some fact, let's do it the smart way. Let's square root both sides and we get cosine x equal to plus or minus the square root of 1/4, which is plus or minus what? 1/2. Which again is a value we recognize as cosine of a special angle. Right? All these questions here are trig functions of known angle equals a value that we should recognize. So cosine equals 1/2 when our reference angle is pi/3. And then Quadrants, again, we get all quadrants here. So we're going to get angles pi over 3. What's the next one that doesn't reduce? 3 pi over 3 definitely reduces. 2 pi over 3, and then what? 4 pi over 3, and then what? 7 pi over 3 would be a little too much. It doesn't reduce, but it's bigger than 2 pi. So these are the 4 angles in quadrant 1, quadrant 2, quadrant 3, quadrant 4, where cosine is either positive 1/2 or negative 1/2, which would mean cosine squared is positive 1/4 because the negative or positive squared. All right, this last one, a little trickier. We have 2 sine squared x plus sine x equal to 1. And though it might be tempting to factor out a sine from here, it's not an excellent idea. It's going to lead you possibly astray. What we're going to do instead is we're going to bring everything to the left. Right, this is 2 sine squared of x plus sine of x minus 1 equal to 0. And what we're going to do is we're going to treat sine like the variable. This is actually a quadratic function, but instead of being quadratic where x is the variable, it's a quadratic where sine is the variable. And it definitely factors. We can do it the long way, but I'm going to do it the short way, meaning there's not a lot of options here. If I was trying to factor 2x squared plus x minus 1 equal to 0, there's only really one choice to make. I know I have to have a 2x and an x to multiply the 2x squared. There's no other way to get there. And then there's only one way to multiply the negative 1. 1 times negative 1. I should say, there's only one way to do it using integers. There's obviously an infinite number of ways to multiply the negative 1 if you use fractions. 2 times negative 1/2, etc. But there's only one way to multiply to negative 1 with integers, that's 1 and negative 1. So I want a 1 somewhere and a negative 1 somewhere. I have to figure out which is which. Well, I want a positive x, meaning I should have a minus here and a plus here. So that when I multiply this out, I get a negative 1x plus a 2x, which adds up to plus x. So if this factors this way, that means this factors this way. 2 sine of x minus 1 times sine of x plus 1 equal to 0. I should have had this flipped. Oh well. That factor is going to give me sine of x plus 1 equal to 0, which gives me sine of x equal to negative 1, which we already solved in the first part, C. That's going to be x equal to 3 pi over 2. But then we also have this factor here equal to 0. So if we have 2 sine of x minus 1 equal to 0, we're going to have 2 sine of x equal to 1. We're going to have sine of x equal to positive 1/2. Okay. So again, I'm looking for the reference angle. The reference angle here is going to be, well, it's not pi over 3 because pi over 3 is where cosine is equal to 1/2. It's definitely going to be pi over 6. My reference angle is pi over 6. And my quadrants, well, I want sine to be positive. That's quadrants 1 and 2. So my angles are actually going to be pi over 6 in quadrant 1 and 5 pi over 6 in quadrant 2. So this equation has 3 answers. Pi over 6, 5 pi over 6, and 3 pi over 2. That's, I mean, there's not a lot else to say about solving trigonometric equations. It's kind of find your trig function equal to some number, And then we have to think about what angle makes that true. So there we go. Make up one more here. Sure, let's try this one. I know I'm throwing in extra pages. I want to give you more questions. Let's say we wanted to solve, let's make it easy. Easy-ish. We'll just factor. So we have 2 times cosine x plus 1 times cosine x plus 1. What if we wanted to solve that? In fact, I'm going to let you guys work on that for a minute. See if you can solve that. You should get 3 different answers, just like the previous one. So I was a little lazy writing this problem in that if I was trying to make it harder, I would have started with saying 2 cosine squared x plus 3 cosine x plus 1 equal to 0. And then I would have had you factor it as well. But definitely the factoring is how we want it so that we can easily solve it. Because whenever you're saying something equal to 0, the reason we're factoring is because then one of the factors has to be 0. Right? It's kind of the only thing that's true. The only kind of multiplication where that's true. If 2 things multiply to 0, one of them has to be 0. If 2 things multiply to 5, we know nothing. Right? There could be 5 and 1, or 2 and 2.5, or 10 and 1/2. Right? There's lots of options. Here, setting this factor equal to 0, we get cosine x plus 1 equal to 0, cosine x equal to -1. And when you see cosine or sine equal to 1 or -1 or 0, that means you're at a quadrantal angle. So I always have to think about, okay, where am I? Cosine's -1, I want to be over here, where the point is -1, 0, and the angle is pi. So pi is my answer to that part of this. And then for this other part, we're saying 2 cosine x plus 1 equal to 0. We're subtracting 1 and getting 2 cosine x equal to -1. We're dividing by 2 to get cosine x equal to -1/2. And then we are going to think about, well, what's our reference angle here? And if it's a sine or cosine equal to 1/2, it's either root pi over 6 or pi over 3. And if it's cosine being 1/2, that means I've gone further in because cosine is smaller, so it's pi over 3. My quadrants are quadrants 2 and 3. So my actual angles are x equal to not pi over 3, but 2 pi over 3 in quadrant 2 and 4 pi over 3 in quadrant 3. Those are my 3 answers: 2 pi over 3, pi, and 4 pi over 3. All right. And then the other thing we're going to do today is a little more practice graphing sine and cosine with some shifts and some stretches and some everything. So let's, yeah, we got time. It's always, there's not always enough time. There's enough time today. So we're going to graph y equal to 2 cosine of 2x minus pi over 3 minus 1. And I do think it's worth writing down what kind of things are going to happen here. So we know that this 2 means that the amplitude is 2. And this minus 1 means we're going to shift down 1. And when I do a shift down 1, I really do like to draw a new middle line. So instead of having my middle line being at 0, I'm going to draw a new middle at -1. In fact, I also know I'm going to be going 2 above that and 2 below. So my kind of important y values here, so you can see that. My importance is 2. There's too much space, too much. My important y values here are going to be 1, -1, and -3. Because I'm shifting down 1 and my amplitude is 2 above that and 2 below that. And now for the x stuff. So I have to figure out what our period is and what our horizontal shift is and what our 5 important x values are. So our period is 2 pi divided by what? 2. Which 2? That one, right? Not the one over here, the one that's multiplied by x. This is 2 pi divided by 2, which is going to be pi. And then I like to think about what a quarter of my period is as well, because all of our 5 points are a quarter of a period apart. So 1/4 of my period is just 1/4 of pi, which is pi over 4. And then we have to figure out what our starting point is, or our phase shift, if you want to use fancier language. Whenever you want to find the phase shift, the easiest way to do it is to set the inside of the trig function, or the angle part of the trig function, equal to 0. So we're going to set 2x minus pi over 3 equal to 0. This will help you avoid the mistake of saying the phase, or that the horizontal shift is pi over 3 to the right. It's not pi over 3 to the right. It's going to be less than that because that 2 is messing up how much shift there is to the right. So if I add pi over 3 to both sides, and then instead of dividing both sides by 2, let's multiply both sides by 1/2. So 1/2 times 2x equals 1/2 times pi over 3. And I'm going to get x equal to pi over 6. That's my phase shift. That is where I'm starting my graph. So I'm starting not at 0, but at pi over 6 and down 1. Oh, except this cosine. That would be where sine started. I thought I had cosine. So I'm actually going to be starting here. That's going to be my first point. It's going to be pi over 6, comma, +1. In case I hadn't made this clear before, these other marks here are each evenly spaced. So if that's pi over 2, this is 1/3 of pi over 2, which is pi over 6. So that really is pi over 6, and that really is pi over 3. If you notice. Okay, so I want to find my other important points. My first point is pi over 6. My second point is going to be pi over 6 plus pi over 4. I need a common denominator. So that's going to be 2 pi over 12 plus 3 pi over 12, which is 5 pi over 12. Let's find our third point. So it's going to be my previous point, 5 pi over 12, plus another quarter of a period, which is pi over 4. But I might as well just write it as a common denominator, right? I know pi over 4 is 3 pi over 12. I just did that work. So let's write it as 3 pi over 12. That's 5 plus 3. That's going to be 8 pi over 12. You can reduce this. It's not really that necessary. It is 2 pi over 3. My fourth point, again, I'm taking the previous point, 8 pi over 12, and adding on a quarter of the period, which is 3 pi over 12, to get me 11 pi over 12. And finally, my fifth and last point is 11 pi over 12 plus a quarter of my period, which is going to get me 14 pi over 12, which, yes, reduces to 7 pi over 6. And if you're really concerned if you've done this right or not, one way you could check is to check that the fifth point minus the first point equals the period. And it does. 7 pi over 6 minus pi over 6 equals 6 pi over 6, which is the period. So that's a way you can check. It's not necessary, you don't have to do that, but if you wanted to do it, you certainly could. All right, so now to try and graph this thing. All right. So I'm going to try and do my best here. So I'm starting at pi over 6, 1, and I'm going to try and find this endpoint over here at 7 pi over 6, 1. Bless you. And now these aren't all nice values here. So 5 pi over 12, you're just kind of stuck, right? It's kind of like right here. So cosine starts at the top and then goes to the middle. And then at the next point, 2 pi over 3, which would be right there, right? Because that's pi over, yep. Be right there. So at that point, and then back to the middle at 11 pi over 12, which is a little bit less than pi, and then back to the top. One thing I will mention here is that you don't have to graph this on a grid that already has things marked out. But I'm trying to be extra precise here because I'm trying to get them like on the spots that are already kind of given to me. But we can graph this without using what we're given. It's also perfectly fine. I do want to mention, right? So this point here, I don't want to label these points. What I want to point out is from here to here, that's pi over 4. And from here to here, that's pi over 4. Pi over 4. Pi over 4. Each of those 1, 2, 3, 4, 5 important points are exactly a quarter of a period away from the previous one. That's how we found them. We took the first one and added a quarter of a period and then added a quarter of a period. We did that 4 times. I think this is the best way to graph sine and cosine. I don't want to graph more points than this for sure, but I do feel like these 5 points are kind of the points you should be graphing when you're graphing sine or cosine. Questions or comments before we do another one? Katie?
Once again, you probably explained.
No worries.
But how did you, from the second point to the third point, why did the period change from pi over 4 to 3 pi? Oh, wait, you just simplified it. Okay.
Right. But so here's what I was doing though. I was essentially saying I've already done this work, right? I already did multiply pi over 4 by 3 over 3 to get 3 pi over 12. And since this thing has the pi over the 12 as the denominator, I'm not going to do this again. I'm just going to, well, I know it's 3 pi over 12, so I'm just going to start there. Which is why once you have a common denominator for this process here, I really do recommend leaving it as that denominator. You don't, I didn't really want to simplify this to 2 pi over 3 or this to 7 pi over 6. I did just to show it, but I would have left it as pi over 6, 5 pi over 12, 8 pi over 12, 11 pi over 12, 14 pi over 12. And those would be perfectly fine values to write on your graph or whatever. I also don't think you need to write those on your graph, right? The graph is already cluttered enough. You can write these up here, totally fine. All right, let's do one more. Let's take a fun one. You can graph y equal to 3 sine of 3 halves x minus 3 pi over 4. All right. So our amplitude is 3. We don't have a vertical shift here. Our period is 2 pi divided by 3 halves. which is going to be 2 pi multiplied by 2/3, which is 4 pi divided by 3. And the quarter of our period is going to be 1/4 times 4 pi over 3. And you can either multiply it out and get 4 pi over 12 and then reduce it, or you can just cancel the 4's right there and say it's pi over 3. So that's a quarter of our period. And then we need to find our phase shift or a horizontal shift, whatever you want to call it. Let me ask you all, are we shifting to the left or to the right? To the right. Okay, we're going to set 3/2 x minus 3 pi over 4 equal to 0. We're always just setting the insides of that thing equal to 0. And then there's a couple things you could actually, I want to bring the 3 pi over 4, but you could totally like multiply everything by 4 first if you wanted to. Or you can get rid of the denominator, that's an option. But I'm going to do it the way I would normally do it. 3/2 x equal to positive 3 pi over 4. And then I'm going to multiply both sides by 2/3. Because I want to isolate x. So I'm going to end up with x on the left and how much pi on the right? 2 pi over 4 or 1/2 pi. An appropriate amount of pi, thanks. Half pi. Too much pi. So pi over 2 is where we're starting. So we're shifting pi over 2 to the right. So there's our starting point. And it actually is the starting point. I'm not graphing the wrong point. Like the sign starts in the middle. So we're going to be middle and then top and then middle and then bottom and the middle. We're going to be going up as high as 1, 2, 3, as low as -1, -2, -3. So our y values we care about are here, 3, here, 0, and -3. Okay, so now we just have to find our next 4 important points. So our first is pi over 2. And the next one's going to be pi over 2 plus a quarter of the period, which is pi over 3. Let's get a common denominator. That's going to be 3 pi over 6 plus 2 pi over 6, which is 5 pi over 6. So my second point is going to be right here. There's 5 pi over 6. And here is my 1/4 of a period, which is pi over 3. And so here's what actually the rest of this one should look like, right? My next point, assuming this is spaced out correctly, which it is, my next point should be right there. And then my next one should be right here. And the last one should be right there. I'm still going to find them, but I just want to kind of show you guys graphically. Oh yeah, they're each just pi over 3 apart from the next one. So this next important point is 5 pi over 6. This next one here, I'm just adding pi over 3 to 5 pi over 6. So 5 pi over 6 plus, instead of adding pi over 3, I'm going to do the math already and say, well, I know that pi over 3 is 2 pi over 6. And that's going to give me 7 pi over 6. Which is definitely the value right there. And then the next one's going to be 7 pi over 6 plus another 2 pi over 6, which is 9 pi over 6, which definitely does reduce to 3 pi over 2, which is certainly the x value I'm getting at this point right here. And then the last one, taking that previous one, I'm taking 3 pi over 2, and I'm adding on a quarter of a period, pi over 3. And getting a common denominator, which I should have done already. It's 9 pi. I should have used the 9 pi over 6, not the 3 pi over 2. I should have used the 2 pi over 6, not the pi over 3. It's 11 pi over 6. And we can see that from our first point to our last point, the total length is 1 full period, because 11 pi over 6 minus pi over 2 is 11 pi over 6 minus 3 pi over 6, which is 8 pi over 6, which reduces to 4 pi over 3, which is our period length. 1 full period. You don't have to do that last part, but I like it as a check. Like, oh yeah, I didn't screw it up. I made all my additions right. My points look good. And yeah, it's 1 period from the first to the last. And then we should draw it. All right.